Pluto's direction has forever been a subject of interest and worry. From the very beginning, Pluto's orbit has converged with that of another planet, which normally brought up issues. Pluto, the mysterious and little divine body arranged in the farthest reaches of our nearby planet group, has turned into a frequent subject of conversation in the field of cosmology. Ongoing discoveries have ignited caution, showing a potential crash with Neptune, a situation that has caught the attention of researchers and space enthusiasts alike. Eminent figures like Neil deGrasse Tyson and Michio Kaku have voiced their concerns over the likely ramifications of this divine encounter. Yet, how did Pluto's orbit lead to a potential crash with Neptune? And what might such an event mean for Earth? Join us as we investigate the complexities of Pluto's journey and why researchers are increasingly worried about this grandiose anomaly. Once hailed as an undeniable planet, Pluto went through a significant renaming as a dwarf planet, primarily due to the whimsical nature of its orbit. Despite its downgrade, Pluto continues to dazzle and intrigue those within the galactic community. Recent alerts from prominent researchers, including Neil deGrasse Tyson and Michio Kaku, have suggested that Pluto's orbit could intersect with Neptune's, raising the potential risk of a collision with sweeping ramifications for our planet. Pluto's orbit around the Sun is remarkable, attributable to its distinctive features. Its orbit is unusually elongated, requiring a staggering 248 years to complete. Since its discovery in 1930, Pluto has not yet finished a full orbit. What makes Pluto especially fascinating is the highly elliptical shape of its orbit, in stark contrast to the nearly round orbits of the major planets. Moreover, Pluto's orbit is tilted at an angle of 17 degrees relative to the ecliptic plane, resulting in a steeper slope than that of other planets. This combination of inclination and the elongated orbit adds complexity to its movement. An especially striking feature of Pluto's orbit is its regular intersection with Neptune's orbit. Every 248 years, during these periods, Pluto's path brings it closer to the Sun than Neptune, which challenges the usual relative positions of the two planets within the solar system. Further analysis reveals that Pluto's orbit is far from perfect. Rather, it follows an elliptical, oval-like trajectory, meaning its distance from the Sun fluctuates significantly throughout its orbit. At its closest point, Pluto reaches about 30 astronomical units from the Sun, but at its farthest, it stretches to more than 49 astronomical units, almost double the distance of Neptune from the Sun. Additionally, Pluto's orbit is tilted relative to the paths of other planets, adding another layer of complexity to its relationship with Neptune. This inclination plays a crucial role in how Pluto and Neptune interact. When their orbits cross, their gravitational forces act on each other, steadily altering their trajectories. This interaction highlights the interconnected nature of the solar system, where the gravitational influence of one body can affect the movement of another. With advancements in observational technology, astronomers have been able to track Pluto's motion with greater precision, leading to a clearer understanding of its orbit and its potential consequences for the overall stability of the outer solar system. While the likelihood of an actual collision between Pluto and Neptune is low, the possibility is still being carefully monitored. Scientists are concerned because the results of such a collision could be catastrophic. Despite its small size and distant location, Pluto remains an object of intense interest for both researchers and space enthusiasts. A key question arises, however. Why hasn't Pluto collided with Neptune yet? The answer lies in the gravitational influence of other planets. Since Pluto's discovery, astronomers have been trying to unravel its orbit. Unlike most planets, which maintain relatively stable orbits along the ecliptic plane, Pluto's orbit stands out due to its steep angle and elliptical shape. The mystery deepened when it became clear that Pluto's orbit crosses Neptune's, presenting a potential hazard. Despite this, Pluto's orbit remains remarkably stable, showcasing the intricate mechanics that govern the movement of celestial bodies. Studying the interactions between Pluto, Neptune, and the Sun presents a formidable challenge for cosmologists. Predicting their movements requires an in-depth understanding of how their gravitational forces affect each other's orbits. To navigate this complexity, scientists use various models, such as Lagrangian libration, scope libration, and the VSOP, von Zippersteves and Kaplan model, to interpret this grand puzzle. For instance, Lagrangian libration plays a key role in maintaining the stability of planetary orbits. When Pluto crosses Neptune's path, it remains at least 90 degrees away from Neptune, preventing a direct collision. Scope libration ensures that when Pluto approaches Neptune or any large planet, it is positioned above their path, reducing the chances of an accident. The VSOP model explains why Pluto's orbit appears erratic yet remains stable over time. Despite the apparent chaos of space, there are underlying patterns that keep everything in balance and prevent Pluto from colliding with Neptune or dramatically altering its orbit. The concept of orbital chaos, which refers to the sensitivity of a celestial body's orbit to its initial position, is clearly evident in Pluto's orbit. Even minor changes in Pluto's position or velocity can have massive effects over long periods. Scientists use advanced computer simulations to model Pluto's interactions with other bodies in space, like Neptune, and to explore the effects of even the slightest shifts in its path. In the 1980s, these simulations revealed an interesting finding. Despite Pluto's orbit appearing stable, it can still behave erratically. A tiny change in Pluto's initial position or velocity could lead to massive changes over time. However, even with these uncertainties, Pluto's orbit remains stable over billions of years, suggesting that, despite its turbulent appearance, it follows an underlying order. The unpredictability of planetary orbits, like Pluto's, makes it difficult to predict long-term changes. These models require extremely accurate initial conditions, as even the smallest data errors can lead to vastly different outcomes, making precise predictions extremely challenging. Understanding Pluto's orbit is crucial, especially when considering the potential for a future collision with Neptune. This data helps astronomers gain a deeper understanding of the mechanics of the solar system. Pluto's orbit serves as a perfect example of how seemingly chaotic paths can ultimately achieve balance. Guided by the forces of gravity and motion, it is essential to continue observing and studying these celestial mechanics to better understand our place in the universe. Pluto's orbit perfectly illustrates the erratic nature of space. Its strange, oval-shaped path leads to periodic intersections with Neptune, making it difficult to predict the long-term dynamics of the system. However, gravitational forces play a crucial role in keeping Pluto and Neptune from colliding. Gravity, which attracts objects to one another, ensures that despite their intersecting orbits, the two bodies generally remain separated. The chance of a collision between Pluto and Neptune, while unlikely, would be a momentous event with far-reaching consequences. Such an occurrence would radically change how we understand the solar system. Despite the remarkable advances in space exploration, Pluto's orbit remains a symbol of the many mysteries that still exist in the universe. Scientists continue to monitor Pluto's trajectory to better comprehend how larger planets influence its movement. This data is essential for understanding the complex relationships between celestial bodies and how their movements can affect one another. Prominent scientists, such as Neil deGrasse Tyson, have speculated that Pluto may one day collide with Neptune. Tyson, a renowned astrophysicist, views Pluto's renaming as a dwarf planet as a pivotal step, acknowledging the importance of further study and observation. He believes that Pluto's unusual orbit highlights the fact that much still needs to be discovered about space and the forces that shape it. According to Tyson, the mysteries of space make studying it so captivating, and he encourages others to delve into the fascinating complexities of celestial mechanics. Along with other experts, Tyson expresses concern about the potential dangers posed by Pluto's eccentric orbit should a collision occur. Among Pluto and Neptune, an impact could prompt devastating ramifications for our planetary group. The energy let out of such an event would be massive, and the flotsam and jetsam dispersed all through space could have sweeping impacts, conceivably in any event affecting different planets and moons. Neptune itself would be impacted, and its circle could change, further confounding the dynamics of the external planetary group. Famous hypothetical physicist Michio Kaku, known for his contributions to string theory, also offers significant insights into space exploration. Kaku believes that concentrating on phenomena like Pluto's orbit is fundamental for understanding the broader principles of celestial mechanics and theoretical physics. He suggests that looking at Pluto's interactions with Neptune can assist researchers with ensuring the security of future space missions. Kaku also stresses the importance of understanding gravitational forces in space exploration, as they could significantly shape how we explore distant worlds. His work in string theory, which aims to explain the fundamental forces of the universe, aligns with his interest in Pluto's orbit. An impact between Pluto and Neptune could provide vital information that would contribute to our understanding of gravity and spacetime. Key to string theory: although such an event would directly affect Earth, it could offer an extraordinary opportunity to concentrate on the behavior of fundamental forces under extreme circumstances. As space exploration continues, the eccentricities of planetary interactions become increasingly evident. The study of celestial dynamics, for example, the complex gravitational relationship between Pluto and Neptune, offers valuable insights into the key laws of the universe. By continuing to monitor and study these phenomena, we draw closer to unraveling the complicated nature of the universe. The gravitational dance between Pluto and Neptune highlights how even distant planets can exert influence over each other. These celestial bodies exert gravitational forces that, over extended periods, can quietly yet fundamentally shape their orbits. While a direct collision remains unlikely, the possibility cannot be entirely ruled out, which keeps researchers and astronomers on alert. Understanding these forces may one day allow us to predict and mitigate the risks posed by such massive events. One captivating aspect of planetary motion is how seemingly irregular or turbulent interactions can result in stable, predictable patterns. This is particularly evident in the case of Pluto, whose orbit may seem erratic but is actually governed by precise gravitational forces. These forces help prevent Pluto from crashing into Neptune, despite the apparent overlap in their paths. The delicate balance between the gravitational pull of other planets in Pluto's orbit keeps the dwarf planet on a steady but complex course. Understanding this intricate relationship is crucial to advancing our knowledge of the broader solar system. As researchers continue to study Pluto's orbit, they also turn their attention to other areas of space exploration. For example, studying systems like TRAPPIST-1, which contains several Earth-sized planets, helps astronomers understand how gravitational forces between planets can lead to orbital resonances. In some cases, these forces can destabilize a planet's orbit, leading to instability. However, the TRAPPIST-1 system is not experiencing any such effects currently. Researchers continue to monitor planetary movements within these crowded conditions to better understand potential risks and their evolution over time. Meanwhile, astronomers are also focused on understanding the behavior of rogue planets, which travel through space without being bound to any star. As our exploration of space progresses, the study of celestial bodies like Pluto and the TRAPPIST-1 system becomes increasingly crucial for expanding our understanding of celestial mechanics. The study of rogue planets, which don't orbit stars, adds another layer of complexity to our understanding of planetary motion. These planets, drifting through space without gravitational connections to any star, provide an interesting challenge for space scientists trying to interpret the various ways planets can behave and evolve in the vastness of space. Their erratic trajectories can introduce new variables into the already complex dynamics of celestial mechanics, and understanding them could offer crucial insights into the formation and development of planets and systems outside our own solar system. The unpredictable nature of Pluto's orbit provides valuable lessons on how celestial bodies can follow seemingly irregular paths yet adhere to deep underlying patterns governed by gravitational forces. Despite its odd elliptical orbit and varied direction, Pluto remains a testament to the precision with which gravity governs planetary motion. By studying such anomalies, scientists are uncovering the governing laws of orbital dynamics and applying them to other celestial phenomena, helping to predict and explain the behavior of distant objects in space. Although the likelihood of a Pluto-Neptune collision is small, the mere possibility keeps space experts on alert. Understanding the gravitational relationship between the two distant bodies and their orbits is crucial for ensuring that future space missions and explorations do not encounter any obstacles. Even though a collision between Pluto and Neptune would likely have minimal direct consequences on Earth, it would still provide a significant opportunity for scientists to observe the functions of gravity and spacetime under extreme circumstances, potentially offering new insights to aid ongoing studies in astronomy. Despite Pluto's unusual orbit, the study of other similar astronomical anomalies continues to provide insight into the many mysteries of the universe. As our technology and observational techniques improve, scientists can refine their models of planetary and orbital behavior. This ongoing research is essential for understanding the intricate dynamics of the solar system and beyond. As each discovery adds to a more complete picture of the universe's behavior, particularly understanding how gravitational forces impact the movement of celestial bodies, it provides critical data for planning future space missions, especially those venturing to distant exoplanet systems or into the outer reaches of our own solar system. One major aspect of Pluto's orbit is its resonance with Neptune. This relationship plays a key role in ensuring the stability of both bodies' orbits. Even though their paths cross every 248 years, the gravitational forces between Pluto and Neptune are in harmony so as to avoid a collision. The delicate balance between their movements is a testament to the precision with which the laws of physics work, even in the most distant regions of the solar system. This resonance prevents any potential accidents, ensuring that the planets continue to coincide without significantly altering each other's paths. This intricate dance between Pluto and Neptune serves as a reminder of the cosmic order that supports even the most tumultuous-sounding orbital mechanics. While Pluto's orbit is far from ordinary, it is a stunning example of how the universe operates with a level of accuracy and order that isn't immediately apparent. Despite its irregularity, the planet's path is influenced by the gravitational forces of nearby bodies, which help maintain its stability. Through continued observation and study, space experts continue to gain insights into how even the most seemingly capricious objects in space can be part of a larger, more organized system. This knowledge allows scientists to better predict the future behavior of objects in our solar system and beyond. As technology advances and our ability to study celestial bodies improves, we can expect to learn even more about the forces at work in space. The study of Pluto's orbit, along with other objects like rogue planets and distant star systems, will remain essential for understanding the vast, complex universe. Through these studies, scientists will not only better understand the mechanics of planetary motion but also learn more about the fundamental forces that shape the universe. The ongoing study of Pluto, Neptune, and other celestial phenomena helps further our understanding of space and our place within it. The unpredictability of planetary interactions, such as the potential collision between Pluto and Neptune, underscores the dynamic nature of space. As astronomers gather more data and refine their understanding of planetary motion, they gain a clearer picture of the forces at play. However, there is still much to discover about how these forces affect celestial objects and how they might change over time. The study of Pluto's orbit, with its intricacies and anomalies, provides a rich field for exploration and offers valuable lessons that extend beyond this particular system. In the years to come, continued advancements in space observation and exploration will likely yield even more insights into the behavior of planets like Pluto and Neptune, and perhaps even uncover new phenomena that challenge our current understanding of the universe. Understanding the interactions between planets, including the delicate gravitational dance between Pluto and Neptune, will not only help us predict their movements but also improve our ability to safely explore the universe. These discoveries will likely shape the future of space exploration and expand our understanding of the universe's vast and complex nature.